Yes, it could damage the 208 volts elevator motor to run it at 208 volts from a delta source. A Y-delta transformer is used to convert a three-phase Y system to a three-phase delta system. The line-to-line voltage of a Y system is approximately 1.73 times the line-to-neutral voltage, while the line-to-line voltage of a delta system is equal to the line-to-neutral voltage. The elevator motor is rated for 200 volts, which is the line-to-neutral voltage in a delta system. If the motor is connected to a Y source, the line-to-line voltage will be 200 volts multiplied by 1.73, which equals 346 volts, and that voltage is significantly higher than the motor's rating. This could cause the motor to overheat and fail. Now let's talk about that weird 139/240 voltage setting. It is possible that the 139/240 voltage setting is a typographical error. The generator manual or the generator manufacturer should be consulted for clarification. However, it is also possible that the generator has a built-in voltage regulator that allows the line-to-line voltage to be adjusted by a certain percentage. In this case, the 139/240 setting may be intended to provide a line-to-line voltage of 240 volts with a line-to-neutral voltage of 139 volts. This setting could be used to reduce the starting current of the elevator motor or to compensate for voltage drop in the feeder. To elaborate further, let's delve into the distinctions between delta and Y configurations in three-phase power systems and how these differences can impact motor performance and longevity. Understanding these configurations is crucial for ensuring the reliable operation of electrical equipment, especially sensitive devices like elevator motors. The Y configuration, also known as the star configuration, features a neutral point formed by connecting one end of each of the three phases. This neutral point provides a stable reference, allowing for both line-to-line and line-to-neutral voltages to be derived. The line-to-line voltage in a Y system is √3 approximately 1.732 times the line-to-neutral voltage. For instance, in a common 277/480 volts Y system, the voltage between any two of the three phases is 480 volts, while the voltage between any phase and the neutral point is 277 volts. This configuration is widely used in power distribution systems because it offers flexibility in serving both three-phase and single-phase loads. In contrast, the delta configuration connects the three phases in a closed loop, without a neutral point. The voltage across any two phases in a delta system is the same as the phase voltage. Delta systems are often used in applications where high starting torque is required, such as in large motors. However, they are more susceptible to voltage imbalances than Y systems. Now consider a 200 volts elevator motor designed for a delta system. In a delta system, the line-to-line voltage is equal to the phase voltage, so each winding of the motor is designed to operate at 200 volts. If this motor is connected to a Y system with a line-to-line voltage of 208 volts, and assuming a direct connection without the appropriate transformation, the motor windings would be subjected to a voltage significantly higher than their rated voltage. This overvoltage condition can lead to several problems. Firstly, it can cause excessive heat generation within the motor windings. The heat is proportional to the square of the voltage, so even a small increase in voltage can result in a substantial increase in heat. If the heat exceeds the motor's insulation temperature rating, it can degrade the insulation, leading to short circuits and eventual motor failure. Secondly, overvoltage can cause increased magnetic saturation in the motor core. This saturation can lead to increased current draw, further exacerbating the heating problem. Additionally, the motor's efficiency can decrease, leading to higher operating costs. Thirdly, the motor's lifespan can be significantly reduced. Continuous operation at overvoltage conditions accelerates the wear and tear on the motor's components, leading to premature failure. Regarding the generator's voltage settings, the presence of a 139/240 setting raises questions. As noted earlier, it could be a typographical error, and it's essential to verify the correct settings with the manufacturer's documentation. However, if the setting is indeed accurate, it could serve a specific purpose, such as reducing the motor's starting current. When a motor starts, it typically draws a much higher current than its running current. This inrush current can cause voltage dips in the power supply, which could affect other equipment connected to the same circuit. Reducing the voltage during startup can mitigate this problem. By reducing the voltage to 139 volts line to neutral and 240 volts line to line, the starting current can be reduced, minimizing the voltage dip. Once the motor reaches its operating speed, the voltage can be increased to its rated value. Another possible reason for the lower voltage setting is to compensate for voltage drop in the feeder cables. When electricity flows through a cable, the voltage drops due to the cable's resistance. The longer the cable and the higher the current, the greater the voltage drop. If the generator is located far from the elevator motor, the voltage drop in the feeder cables can be significant. By setting the generator's voltage slightly higher than the motor's rated voltage, the voltage at the motor terminals can be maintained at the correct level. In conclusion, it is essential to ensure that the voltage supplied to an elevator motor matches its rated voltage and that the power source is properly configured. Connecting a motor to the wrong voltage or a mismatched power source can lead to serious damage and premature failure. Always consult the motor's nameplate and the generator's documentation before making any connections. If there is any doubt, consult a qualified electrician to ensure that the installation is safe and compliant with all applicable codes and standards. Additional information about power systems can be helpful to understand. Power systems are complex networks designed to generate, transmit, and distribute electrical energy efficiently and reliably. These systems are typically divided into three main components: generation, transmission, and distribution. Generation involves converting various forms of energy, such as fossil fuels, nuclear energy, and renewable sources, into electrical energy. Power plants use generators, which are electromechanical devices that convert mechanical energy into electrical energy. These generators are typically three-phase synchronous machines that produce alternating current. Transmission involves transporting electrical energy from power plants to substations over long distances. Transmission lines are high-voltage cables that carry electricity at voltages ranging from 115 kV to 765 kV. High-voltage transmission is more efficient because it reduces current and minimizes losses due to resistance. Substations are facilities that step down the voltage of electricity from transmission levels to distribution levels. They also contain equipment for switching, protection, and control. Distribution involves delivering electrical energy from substations to end users, such as homes, businesses, and factories. Distribution lines are lower voltage cables that carry electricity at voltages ranging from 4 kV to 35 kV. Transformers are used to step down the voltage to the levels required by end users, such as 120 volts and 240 volts for residential customers and 480 volts for industrial customers. Power systems must be designed to meet the varying demands of electricity consumers. Load forecasting is used to predict future electricity demand, and power plants are dispatched to meet this demand. Power system operators monitor the system in real time and make adjustments as needed to maintain stability and reliability. The stability of a power system refers to its ability to maintain voltage and frequency within acceptable limits during disturbances such as faults and load changes. Power system protection involves using relays and circuit breakers to detect and isolate faults, preventing them from spreading and causing widespread outages. Power quality refers to the characteristics of the voltage and current that are delivered to end users. Poor power quality can cause equipment malfunction, damage, and reduce lifespan. Power quality problems include voltage sags, voltage swirls, harmonics, and transients. Modern power systems are becoming increasingly complex due to the integration of renewable energy sources, such as solar and wind power. These sources are intermittent and variable, which can pose challenges for power system operators. Smart grids are being developed to address these challenges. Smart grids use advanced technologies such as sensors, communication networks, and control systems to improve the efficiency, reliability, and security of power systems. These grids allow for real-time monitoring and control of the system, enabling operators to respond quickly to changes in demand and supply. Power factor is the ratio of real power kilowatts to apparent power kilovolt amperes in an alternating current circuit. It is a measure of how effectively electrical power is being used. A power factor of 1.0, or 100%, indicates that all of the power being supplied to a circuit is being used to perform useful work. A power factor of less than 1.0 indicates that some of the power is being wasted. Low power factor can result in several problems, including increased energy costs, reduced equipment capacity, and voltage drops. Utilities often charge customers with low power factors a penalty fee. There are several ways to improve power factor, including using power factor correction capacitors and reducing reactive loads. Power factor correction capacitors are devices that store electrical energy and release it back into the circuit, reducing the amount of reactive power being drawn from the utility. Reactive loads, such as motors and transformers, consume reactive power, which does not perform useful work. Reducing these loads can improve power factor. Harmonics are distortions of the sinusoidal waveform of alternating current. They are caused by nonlinear loads, such as electronic devices and variable frequency drives. Harmonics can cause several problems, including overheating of equipment, increased energy losses, and interference with communication systems. There are several ways to mitigate harmonics, including using harmonic filters and reducing nonlinear loads. Harmonic filters are devices that block or reduce the amplitude of harmonic currents. Reducing nonlinear loads can also reduce the generation of harmonics. Transients are short-duration, high-amplitude disturbances in the voltage or current waveform. They can be caused by lightning strikes, switching operations, and equipment failures. Transients can damage sensitive electronic equipment. There are several ways to protect equipment from transients, including using surge suppressors and transient voltage surge suppressors. Surge suppressors are devices that limit the voltage across a circuit to a safe level. Transient voltage surge suppressors are devices that divert transient currents away from sensitive equipment. Grounding is the process of connecting electrical equipment to the earth. Grounding provides a low impedance path for fault currents, protecting people and equipment from electrical shock. Grounding systems must be properly designed and installed to be effective. Bonding is the process of connecting different metal parts of an electrical system together. Bonding ensures that all metal parts are at the same potential, reducing the risk of electrical shock. Bonding systems must be properly designed and installed to be effective. Electrical codes and standards are sets of rules and regulations that govern the design, installation, and maintenance of electrical systems. These codes and standards are designed to protect people and property from electrical hazards. In the United States, the National Electrical Code, or NEC, is the most widely adopted electrical code. Electrical inspections are conducted to ensure that electrical systems comply with applicable codes and standards. Electrical inspectors are trained and certified to identify electrical hazards and ensure that electrical systems are safe. Arc flash is a dangerous electrical phenomenon that can occur when a short circuit creates a high-temperature arc. Arc flash can cause severe burns, blindness, and even death. Arc flash hazards must be identified and mitigated to protect workers. Arc flash studies are conducted to determine the potential arc flash hazards in an electrical system. Arc flash protection measures include using personal protective equipment, such as arc-rated clothing and face shields, and installing arc flash mitigation devices. Electrical safety training is essential for workers who work on or near electrical equipment. Electrical safety training teaches workers how to identify electrical hazards, how to use personal protective equipment, and how to follow safe work practices.